Good morning. Today, I'd like to start looking at how to distinguish whether or not a space is flat or non-flat. The way that we want to do this is that we want to use only considerations that somebody who is within the space itself could calculate and measure. Imagine that I have 4 points in a flat plane, P, Q, R, and S. If I have a vector in a flat plane, then I can parallel transport that vector from any point to any other point without changing the vector any. If I'm using non-flat coordinates, though, the components of the vector will change because the basis vectors will also change. I'm going to call the coordinates of point P by P mu. In relativity, the mu could be 0, 1, 2, or 3. In geometry problems, it might be 1 or 2, or 1 or 2 or 3. The coordinates of point Q, I'll call Q mu. These will differ from the coordinates of P mu by some amount. I'll call those numbers A mu. If we were in a flat space and using flat coordinates, those numbers A mu would be the components of the vector starting at P, ending at Q. If this were a flat space with flat coordinates, these B mu numbers would be the components of the vector that goes from P to R. If I travel from P to Q and then from Q to S, or if I travel from P to R and then from R to S, I end up at the same point. Even with curved coordinates, the vector, when I arrive at point S, being the same vector, must have the same components regardless of which path I took. I'll call that first way of doing it path 1, and the second one path 2. The thing to emphasize is I have to end up with the same vector at point S. Regardless of what the basis vectors are there, the components must be the same. This is going to get very complicated, so I've decided that I'm going to typeset the calculations in order that it be more legible. This is rather labor intensive, but it's better than doing this by hand. The first thing we have to do is let's write the vector v at point S in terms of quantities at point Q in a way that's reminiscent of Taylor series expansion. V at S is V at Q plus some quantity that represents the rate of change of V at Q times how much I'm changing the various variables. Except for the fact that I may have as many as 4 coordinates now, this is the directional derivative from third semester calculus. Well, that and the fact that I have to use covariant derivatives. This is accurate to first order in differential approximation. Also, though, I can think of the vector v at point Q as being approximately the vector at point P plus the directional derivative of v, component number alpha at P, times how much I change the coordinates when I go from point P to point Q. The tricky bit is that the directional derivative component beta of v at Q is typically a complicated function of all of the variables, so I have to take the directional derivative of it. Now, all of the quantities on the right-hand side of the equation are evaluated at point P, So I'm going to stop writing things like v at p and delta alpha v at p. If I don't specify where I'm evaluating something at, it's understood now to be at point P, the point that we started at. All of this is along that first path. To get what happens on the second path, I'm simply going to interchange the A and the B quantities to change the order in traveling from P to Q and then to S, as opposed to traveling from P to R and then to S. Some terms are the same in the two equations. If I subtract the results that I got from one path from the other, I find out that 0 has to be delta alpha, delta beta, v, a alpha, b beta, minus delta alpha, delta beta, v, b alpha, alpha beta. This needs to be true for all possible choices of vector v in whatever space we're working in. At first glance, this doesn't seem so bad, but it turns out to be kind of horrible, though. I'm going to have to figure out what does it mean for v mu semicolon beta semicolon alpha minus v mu semicolon alpha semicolon beta to be 0 no matter what the vector v is. If we were using flat coordinates, the covariant derivatives would just be ordinary partial derivatives, and this would automatically be true. To get started in this calculation, I need to remember something. The numbers v mu semicolon beta are the components of a 1-1 tensor. It's the covariant derivative of the vector v. If I want, I can just write that as v mu beta, leaving the semicolon out, to emphasize the fact that it's a 1-1 tensor that we're looking at. We know how to do the covariant derivative of a 1-1 tensor from our previous work. This doesn't look so bad yet. When I have an upstairs index and I do the covariant derivative, I pretend that it's a vector index. And when I have a downstairs one, I pretend that it's a one-form index. So if I write out what v alpha semicolon beta semicolon alpha is, I'm just taking the alpha component covariant derivative of v mu beta and then putting in the vector-like term and the one-form-like term. If you actually write out what all of that is, you see that it's beginning to get kind of nasty looking, especially that first term. The first term inside the parentheses consists of two other terms. The first one I'll just have to differentiate. The second one, though, is a product of two things, so I'm going to have to apply the product rule to figure out what v mu semicolon alpha semicolon beta is. I'll just take the formula that we just obtained and interchange alpha and beta. When I calculate the difference of these two covariant derivative components, a lot of stuff will cancel out. For purposes of reference, in the first equation, I'm going to call the terms on the right as 1, 2, 3, 4, 5, and 6. The terms on the right in the second equation will be A, B, C, D, E, F, and G. Term 1 is the same as term A because ordinary partial derivatives commute. Term 3 is the same as term D. Term 4 is the same as term C. Terms 6 and 7 are equal, respectively to terms f and g because the Christoffel symbols are symmetric in the two lower indexes. As a result, a lot of things cancel out, and we're left with a somewhat less monstrous looking formula. If you look at the two quantities inside the parentheses on the right, in the first term of each of them, kappa is an index of summation, and the letter nu does not appear. Therefore, in the first two terms, in the first two parentheses, that is, I'm going to stop calling the index of summation kappa and replace it with nu. The reason for doing that is it will let me factor the vector components out now. The condition for flatness is that for all vectors, the difference of these two second-order covariant derivatives should be r mu beta alpha nu v nu. These numbers must always be 0 no matter what the vector v is. The usual for all vectors argument will then tell me that the numbers r mu beta alpha nu must all be 0 themselves. These numbers are called the components of the Riemann Christiffel curvature tensor and will figure prominently in what's to come. Before I wrap this up for today, I want to think about what's going to be in these components. In particular, I want to think about those first two terms. I have partial derivatives of the Christoffel symbols. That means in the enormously complicated mix, there are going to be metric tensor components. There's going to be partial derivatives of those. There's also going to be second partial derivatives. Those are the ingredients that we have previously decided are necessary to cook up the Einstein tensor. So this curvature tensor is definitely going to be connected to the Einstein tensor in some way. We have a good way to go before we see how that connection actually works out. In the meantime, I hope everyone's having a good day, and I'll talk to you again soon.